Imagine a world where objects can change shape and function on demand. This is the promise of 4D printing, a revolutionary technology that takes 3D printing to a whole new level. While 3D printing creates static three-dimensional objects, 4D printing introduces the element of time. This means that 4D printed objects can transform themselves over time, responding to external stimuli like heat, light, or water. These materials have the remarkable ability to change their properties or shape in response to specific triggers. Imagine a pipe that expands or contracts based on water pressure, or a medical implant that adjusts its shape to fit a patient's body perfectly. From self-assembling furniture to self-healing infrastructure, the possibilities are limitless. As we delve deeper into the world of 4D printing, we'll explore the fascinating materials and applications driving this transformative technology. At the heart of 4D printing lies the captivating concept of self-transformation. Imagine a flat sheet that folds itself into a complex origami structure, or a flexible material that morphs into a predefined shape when exposed to water. This magical transformation is made possible by stimuli-responsive materials, the building blocks of 4D printing. These intelligent materials are designed to react to specific external stimuli. Heat, for instance, can cause certain polymers to contract or expand, while light can trigger a chemical reaction that alters a material's form. 4D printing allows for the precise arrangement of different materials with varying properties. This strategic arrangement creates pathways for the material to respond to stimuli in a pre-programmed manner. Imagine a 4D printed object with embedded layers that expand or contract at different rates when exposed to heat. This ability to program self-transformation opens up a world of possibilities. 4D printing takes material science to a new level by embracing the power of multi-material design. Imagine printing an object with intricate internal structures where each component is made from a different material with unique properties. Multi-material design allows engineers and designers to combine the strengths of various materials within a single printed object. For instance, a flexible hydrogel could be combined with a rigid shape memory polymer to create a structure that is both adaptable and strong. This fusion of properties expands the design possibilities and functionality of 4D printed objects. Imagine printing a robotic gripper with soft, flexible fingers that can gently grasp delicate objects, while the palm remains rigid and strong for support. This intricate interplay of materials would be impossible to achieve with traditional manufacturing methods. Multi-material 4D printing unlocks the potential to create objects with unprecedented complexity and functionality. The magic of 4D printing comes to life through the use of remarkable materials like hydrogels and shape memory polymers. Hydrogels are water-loving polymers that can absorb and retain significant amounts of water while maintaining their structure. Think of them as tiny sponges that can swell or shrink in response to changes in humidity or temperature. This responsiveness makes hydrogels ideal for creating 4D printed objects that can change shape or size in response to their environment. Shape memory polymers, on the other hand, have the remarkable ability to remember their original shape even after being deformed. When exposed to a specific stimulus, such as heat or light, these polymers can revert back to their pre-programmed shape. This property makes them ideal for creating 4D printed objects that can transform on demand. Researchers at MIT and Harvard have been at the forefront of developing and exploring the potential of these materials for 4D printing. Section 5, Revolutionizing Healthcare, 4D printing in medicine. The medical field is on the cusp of a revolution, thanks in part to the transformative potential of 4D printing. Imagine medical implants that can adapt to a patient's body over time, or drug delivery systems that release medication with precise timing. One groundbreaking application is the development of self-adjusting stents. Traditionally, stents are made from metal mesh and remain a fixed size once implanted. However, 4D printed stents can be designed to expand or contract over time, adjusting to the patient's artery and promoting better blood flow. Another exciting application is in the field of personalized medicine. 4D printing enables the creation of customized implants and devices tailored to a patient's unique anatomy and needs. This level of personalization could lead to more effective treatments and faster recovery times. Section 6. Reaching for the stars: 4D printing in aerospace. The aerospace industry is constantly seeking innovative materials and manufacturing techniques to push the boundaries of exploration. 4D printing has emerged as a game changer, offering the potential for lighter, more adaptable spacecraft and components. One exciting development is the creation of 4D printed fabrics that can change shape in response to temperature or pressure. NASA has been exploring the use of these fabrics for creating adaptive spacesuits that can adjust to different environments and provide optimal comfort and protection for astronauts. Imagine a spacesuit that can automatically tighten in areas exposed to extreme cold or loosen up to allow for greater mobility during spacewalks. This level of adaptability would be crucial for future missions to Mars and beyond. Section 7. Building the future: 4D printing in construction. The construction industry is ripe for disruption, and 4D printing is poised to revolutionize the way we design and build structures. Imagine buildings that can adapt to changing weather conditions, bridges that can repair themselves, or pipelines that can adjust their diameter based on flow rate. One promising application is the development of self-assembling structures. Researchers are exploring the use of 4D printing to create building components that can unfold and assemble themselves on site, reducing construction time and labor costs. This could revolutionize disaster relief efforts, allowing for the rapid construction of shelters and other critical infrastructure. Beyond self-assembly, 4D printing could lead to the creation of buildings that can adapt to their surroundings. As Section 8. The future of fashion: 4D printing in textiles. The fashion industry is known for its constant pursuit of innovation and cutting-edge materials. 4D printing is making its mark on the runway, offering the potential for garments that can adapt to the wearer's body, environment, or even mood. Imagine clothing that can regulate body temperature, change color, or even transform its shape on demand. 4D printing can create fabrics with embedded sensors and actuators that respond to changes in temperature, pressure, or even light. In the realm of sportswear, 4D printing can create shoes that adapt to different terrains or athletic wear that provides targeted compression or ventilation. This level of customization could significantly enhance athletic performance and recovery. Section 9. Challenges and opportunities: the road ahead for 4D printing. While 4D printing holds immense promise, several challenges remain before it becomes a mainstream technology. One of the main hurdles is the limited availability of programmable materials. Developing new materials that can respond to a wider range of stimuli and exhibit more complex transformations is crucial for expanding the applications of 4D printing. Another challenge is the scalability of production. Currently, most 4D printing techniques are limited to creating small-scale objects or prototypes. Developing methods for large-scale production of 4D printed objects is essential for widespread adoption in industries like construction and manufacturing. Despite these challenges, the future of 4D printing is bright. Section 10. A world transformed: envisioning the impact of 4D printing. The advent of 4D printing has the potential to transform our world in profound ways. From self-assembling furniture to self-healing infrastructure, the possibilities are limited only by our imagination. As 4D printing technology matures, we can expect to see a paradigm shift in manufacturing, moving away from mass production and towards mass personalization. Objects will no longer be designed and manufactured as static entities, but as dynamic systems that can adapt and evolve over time. Imagine a world where products are designed for disassembly and reuse, reducing waste and promoting sustainability. 4D printing could enable the creation of products with multiple life cycles, where materials can be reprogrammed and transformed into new objects at the end of their useful life. As we enter the era of 4D printing, we are embarking on a journey that will redefine the boundaries of design, engineering, and innovation. Please like, subscribe, and comment to stay updated with the latest in 4D printing technology.